Okay, I get a clear sign here that we can start. Everybody's here. Thank you all for joining us today. I welcome to this dissertation and public defense in computer and system science. My name is Mårten Sjöström, for whom of you who don't know that, and I've been honored to chair this session. First, I'd like to welcome the respondent, who is the main figure here today and the reason for us to be here. It is Elijs Dima. He has a bachelor, a master, and a technical licentiate from Mid-Sweden University in 2013, 15 and 18 respectively. He has taken part in 7 visits to different academic industrial partners in Finland, Sweden, Germany, Poland, the UK and Portugal. And he has been involved in 4 research projects with industrial partners. He's also been assisting in teaching in several master and bachelor courses. Secondly, I'd like to welcome the second main figure today, which is the opponent. This Associate Professor Charalambos Poullis. He got a PhD in 2008 from University of South California, and then he's been a lecturer and assistant professor at University of Cyprus and Cyprus University of Technology. And he is now, since 2015, an associate professor at Concordia University in Montreal, Canada. And we welcome you here today, and we're very happy that you can join us all the way from Canada today. He has research interest in the intersection of computer vision and computer graphics, with the goal of create virtual worlds indistinguishable from real world and their use in wide range applications, which is a very interesting area and very much related to what Elijs has done. With us today we also have the examination board with the following distinguished members. We have Professor Patrick Lecaillé. He has been an assistant professor in Technical Institute of University of Nantes back in 97 to 99, and a lecturer at the Technical Institute of University. And since 2003 he's at the École Polytechnique de l'Université de Nantes. And since 2006 he's the head of Image and Video Communication Group at CNRS IRCCYN. His research interests are in visual perception understanding, visual attention modeling and application, as well as image, video and 3D quality assessment and data hiding. Also very relevant to the work today here. Welcome. Further, we have examination board member Professor Aljosa Smolic. 2001 he's got his PhD from Aachen University, and then he was a scientific project manager at Fraunhofer HHI in Germany. He continued, he was also then an associate lecturer at the Technical University of Berlin, and later on he moved on to be a senior researcher scientist at Disney Research in Zurich, Switzerland, where he also was associate lecturer at the ETH Zurich. Since 2016 he is a SFI research professor of creative technologies at Trinity College in Dublin in Ireland, and he's also co-founder of a spin-off company. His research interests are in multimedia and light field processing and compression, which is also highly relevant for today's dissertation. And the last member of the examination board is Professor Assarsson. He's got a PhD in 2003 from Chalmers University of Technology. He's been a postdoc in INRIA in France and had different positions at Chalmers University until 2017. He became a full professor at Chalmers, and he also has created several spin-offs in the area of his research, which is free view video, AI for 3D reconstruction and global illumination, sparse voxel DIGs, shadow algorithms, parallelism, and GPU algorithms, and GPU ray tracing. Also very high relevant today. So additional persons here today, the main supervisor, that's me. I am here since 2001 and founded the research group Realistic 3D. Co-supervisor is Dr. Roger Olsson, who's also been working here a long time at Mid-Sweden University. He is a senior researcher at Mid-Sweden University since 2010. Outline for the dissertation act today is that the opponent will give a brief introduction to the field, which is about 10 minutes, and then the respondent, Elijs, will make a summary of the thesis. And then we'll have a short break, 5 to 10 minutes. We'll rearrange a little bit here, where after the opponent and the respondent will have a discussion led by the opponent. When they have finished the discussion, which usually takes about 40 to 60 minutes, but may continue as long as they wish, the examination board has the opportunity to pose further questions to the respondent. And then after that, all of you who are very eager to pose questions from the audience are welcome to do so, and we will let you in one by one, and you can raise your hand or pose a question in the chat room. After that, the examination board will hold a meeting and to decide the verdict of the defense and the thesis, which is either pass or not pass. Now I turn to you, Elijs, and I ask you if there are any errors of forms in the thesis that you would like to add and correct.
Yes, so unfortunately there is one thing that I have to mention. In the distributed thesis copies on pages 13 and 14, there is one reference that was misprinted as a question mark. That reference should be BOU 16, referring to the camera calibration toolbox by Jean-Yves Bouguet. Possibly I mispronounced that name.
Okay. We will add that to an errata to that later. Okay, then I give the word to the opponent to give a brief introduction to the field.
Of course. First, thank you very much for the introduction. So the work that is about to be presented today evolves around augmented telepresence and the related challenges and limitations. So let us first define augmented telepresence. So the first term, augmented, refers to augmented reality, or AR for short. So this is a technology that provides the user with an augmented or enhanced version of the real world environment. There are two main flavors of this technology. You have immersive AR, where the user wears an AR headset and sees the world through clear lenses. And on the other hand, you have the mobile AR, where the user sees the world through a mobile device, such as a smartphone or a tablet. In both these scenarios, AR enables interactive experiences with the real world by enhancing or annotating real objects with digital content rendered from the point of view of its user. So in the case of immersive AR, the digital content is projected onto the user's lenses. And in the case of the mobile AR, the digital content is overlaid on the video itself shown on the mobile device. So in short, you can think of augmented reality as a real life experience. It is physical reality, augmented with digital content, and hence the name. Going back to the second term, the telepresence. Telepresence is a technology that gives the feeling to the user of being present at a different, distant, remote location. In its simplest form, telepresence can be a live video streaming of another location. However, in this work that Mr. Dima will be presenting, telepresence is used to refer to immersive telepresence and augmented telepresence. So in other words, it includes the capture of the remote location and the transmission in a way that will allow a user to be immersed into that remote location. So to perceive it as if they were within the environment and were able to interact with it in real time. Mr. Dima's work is in this area of augmented telepresence and its application to industrial contexts. Now, the design and development of a system that enables augmented telepresence involves overcoming many challenges relating to the capture, transmission, rendering, and quality of experience. First, one has to address the calibration of a multi-camera setup or system. Although the calibration of a single camera or even multiple cameras is a well-studied problem with many solutions, it is oftentimes that the accuracy is insufficient of what is required for applications such as augmented telepresence. assuming calibration is adequately addressed, then there is a problem of synchronization. Unless a hardware solution is used to trigger the cameras at the same time, there is no guarantee that the cameras will capture an image at the same time. So these may lead to erroneous results in cases where the scene is non-rigid, when you have things moving. Finally, for an end-to-end augmented telepresence system to be useful, one has to develop techniques for efficiently processing, transmitting, and rendering the captured data in such a way that it enables low latency real-time applications. Mr. Dima's work addresses all these issues. And to summarize the objective of his work, it is twofold. First, to address technical challenges relating to multi-camera capture, rendering, and the development of end-to-end systems that enable this augmented telepresence. And secondly, to evaluate the quality of experience of said systems. With that, I think I will stop here and let Mr. Dima present his work.
Thank you very much, Professor Poullis. So I will give the word to respondent Elijs Dima to present a summary of your 4 years work or plus or whatever.
4 years plus,
okay.
With a big plus, yes. So thank you for that very concise summary of essentially what is going to be presented in this presentation as well. So good afternoon or good morning, everyone, and thank you for joining to this defense seminar. I would like to take this chance to summarize and present my work within the topic of augmented telepresence based on multi-camera systems. Now, today's presentation will follow this outline in broad strokes. First, we will cover the basic context and motivation behind choosing to focus on multi-camera systems and why we are focusing on augmented telepresence. Then we will cover the main goals and research outline of my work. After that, we will go into the individual contributions and give a brief summary on those specific ones. For the time being, don't worry about the specific titles. We will get into those details a bit later. And once we are finished with the contribution details, then I will conclude this with a bit of reflection and a discussion on things like future work. So, of course, the first question that comes to mind is, why should we focus on multi-camera systems? Well, there are several good reasons to do so. First off, multi-camera systems are already widely used in many aspects of modern life. For instance, surveillance systems are nowadays largely based on multi-camera systems that allow the surveillance systems to observe the same area from various viewpoints to obtain more detail about the examined environment. Also, multi-camera systems are very extensively used in robot and machine vision for autonomous self-location, environment mapping, and self-driving applications. Further, special multi-camera systems are useful for recording 3D scenes of various events and interactions, which then can be ported over to more widespread uses, such as production of cinematic effects for conventional and for 3D cinema, as well as using multi-camera systems for capturing 360-degree videos. So from these examples, I hope it's more or less clear that multi-camera systems already are and likely will be intrinsically connected to many aspects of our lives. Now, these systems are particularly useful for recovering a more complete view of our environment or a specific remote location. And this makes multi-camera systems suitable for creating mixed reality applications. Now, mixed reality itself is a fairly broad term that covers everything between a completely virtual reality and a completely real reality. And augmented reality is one subset of this reality-virtuality continuum. Now, when we combine augmented reality with telepresence, we gain the property that a remote location is being observed and potentially interacted with in at least close to real time. And then from the augmented reality aspect, we gain the property that this observed location is somehow altered or augmented when shown to the user. This means that augmented telepresence technically denotes immersive video-based communication applications that use view augmentation on the presented output. So in general, various industries are increasingly working towards more and more automation and remote operation. The digitization of various working environments within industries also means that there's a greater use of multi-sensor systems and also the application of virtual and mixed reality solutions. For instance, in construction and mining industries, virtual reality simulators are often used as a way to provide worker training for routine tasks and emergencies without the associated risk that would be incurred by having the workers actually on site on that remote location. Similarly, immersive telepresence interfaces are more and more common for remote control, for controlling specialized vehicles, cranes, also robotic arm-type manipulators. Overall, this shows that there is both interest and activity around the topic of augmented telepresence. So that covers the broad context and the motivation behind my work. So now we will move to the specific goals and the research outline of what I have been looking into. So as mentioned before, augmented telepresence is relevant for non-entertainment applications, and it can potentially provide benefits for worker safety and also work effectiveness. However, augmented telepresence is fundamentally affected by how precisely the remote environment can be captured. Also by various constraints imposed by the sensors used during capturing, and also augmented telepresence is affected by constraints set by the target application. For example, a limitation on presentation timeliness or a limit on how accurately the actual remote environment needs to be displayed. Further, when we are also considering the user of these applications, the experience of augmented telepresence systems is affected by the type of augmented information attached in the scene view, the type of immersive rendering that we select, the choice of presentation devices that we use, and of course the interaction of these various elements. So from my perspective, the overall purpose of this work has been to explore multi-camera based augmented telepresence in these two directions. So first off, how should multi-camera and multi-sensor systems be designed to enable multi-view capture and augmented telepresence applications? And secondly, how is user experience affected when we are applying augmented telepresence in specific task-based industry-inspired scenarios? So these questions lead me to the research outline. Now, in principle, augmented telepresence systems, also end-to-end systems, they can be considered to contain some type of a multi-camera system for capturing the remote environment, some kind of view rendering system for introducing augmentations into the presented view, and some kind of a presentation system to actually convey that generated information to the application user. Now, when we combine these end-to-end systems with specific application contexts that inform both constraints and task metrics for these systems, then we can arrive at the resulting user experience for such end-to-end systems. So with that in mind, here are the specific contributions that we will discuss today that relate to different parts of this structure. So first off, we have investigated camera calibration as part of the multi-camera system design question. Secondly, we have looked at the synchronization between various sensors, or more specifically, we have looked at the consequences of incorrect synchronization in multi-camera systems. Next, we have considered the design for multi-camera based end-to-end systems, where we have been focusing on the ability to do low latency video processing and streaming, which are inherently required for telepresence. After that, we have introduced a specific application context, in this case, underground mining, and we have investigated mainly the processing and system design aspects for augmented remote operation. And finally, we have also included the user experience factor and investigated how certain aspects of augmented telepresence affect the resulting quality of experience of the user. So these 5 are the main contribution topics that today's presentation will focus on. And with that, we can move on to the first contribution, which is camera calibration for multi-camera systems. Now, in principle, camera calibration is the process of creating a mapping between the 3D world recorded by a camera and the 2D image within that camera. And this mapping is typically represented by a camera model. There are various camera models. However, from the perspective of multi-view geometry and also computer graphics, the pinhole camera model seems to be the most widely used. And this pinhole camera model depends on intrinsic and also extrinsic camera parameters to describe the internal properties of a camera and its rotation and translation within some world coordinate system. And then these properties are used to generate a projective transform that maps a location in 2D space to a location in 3D space. So then we can say that calibration is the process of finding or estimating these necessary parameters from the scene capture performed by cameras. In very broad terms, these 3 steps can be found in most calibration solutions. First, specific points of interest are found in the scene. Next, the projections of these points are matched from camera to camera. And then the projection parameters, or the camera parameters, are estimated and progressively refined based on the minimization of the reprojection error. And this reprojection error, it's essentially the distance between an observed point in a camera image and that point's projected pair coming in from another camera's image. Of course, this is in the context of at least a 2-camera system. So camera calibration is a rather densely researched area already. There are well-established calibration solutions that are commonly used. They are found in computer vision libraries and tools such as OpenCV and MATLAB and so on. So in that sense, calibration could be considered as a solved problem. And also the majority of research focusing on calibration seems to seek to improve either the identification of calibration targets, the detection of feature points that will be used for performing the calibration operation, or they focus on the automation of this whole process to make it more feasible for real-world applications and autonomous use. However, what is less explored is this question. How accurate are these commonly used calibration methods at recovering the actual camera parameters and not the reprojection error? So to find an answer to that question, we created a multi-camera system that gave hard constraints on the ground truth of the camera parameters. So 3 cameras were mounted on a programmable moving dolly, and they were moved to specific positions to create a calibration dataset of 15 viewpoints, so 15 virtual cameras. And within this dataset, every row of cameras had the same intrinsic parameters because they were captured by the same camera with the same lenses. And between every row, there was a fixed distance and fixed rotation, leading to identical displacement and relative rotation between the rows and the views. So in other words, we have a scenario where we have ground truth constraints without needing to estimate those ground truth parameters in the first place. This dataset then was given to a set of publicly available calibration tools to see how far the resulting estimations would stray from these ground truth constraints. So here's a sample of some of the results we obtained using our 4 calibration methods. And here we see the estimated relative distance between these cameras. Now, ideally, each of these relative distances, D1 and D2, would remain the same between various viewpoints. However, the wider range of estimates in this method, for example, indicates a worse ability to recover the ground truth camera parameters. So we did similar consistency comparisons between methods for the relative orientations, lens distortion parameters, and specific positions of cameras within this dataset. From the experiment results, we could conclude that none of the tested calibration methods were completely accurate with respect to the ground truth. And this highlights a difference between using a point reprojection error and parameter estimation error as the suitability criteria for selecting or approving a calibration method. Also, of these tested methods, we did not see a systematic difference between target-based and target-less methods as a whole. Specific methods that we tested that were based on structure from motion toolchains, they performed about as well as the tested version of the standard calibration method that is often used also in libraries such as OpenCV. So moving on to the next contribution, which is still in the multi-camera system domain, but this concerns camera synchronization. So in an ideal case, all cameras in a multi-camera system would be perfectly synchronized, meaning that all cameras take an image of the scene at exactly the same time. However, there are many cameras, such as surveillance cameras, time-of-flight cameras, low-cost cameras, that cannot be perfectly synchronized at the hardware or sensor exposure level. Now, this lack of perfect synchronization, it might or might not be a problem. In principle, synchronization only matters if we are recording a scene with moving elements. So, for example, we have this red object moving at a speed no greater than max v, and it is at these specific positions at these time instants. And suppose we have a 2-camera system with some synchronization or error between these, and these cameras observe this object at these specific rays, which map this object to a specific position in the camera image. If we ignore the synchronization error or the capture time difference, then trying to triangulate the object's coordinates will lead to inaccurate results. Because in the recorded data, if we ignore this synchronization error, we have a somewhat incorrect guess at the actual position of the recorded object. Now, again, depending on the application, this positional difference can have different consequences. And the problem is that in order to decide whether a synchronization error is acceptable or not for a specific purpose, we need to know how this synchronization error relates to the error in object position estimation, or in other words, how synchronization error relates to a depth error. And from a multi-camera system design perspective, we would like to know how a camera arrangement would affect this range of depth errors that we get. So here we need to introduce a new term, depth uncertainty, delta D, which essentially is the maximum range of depth variation of an observed moving object from the perspective of one captured time frame. From a little bit of geometry, we can find that this range in 2D space by assuming object trajectories that essentially maximize depth uncertainty along the investigated ray. And we can find this depth uncertainty as long as we have some assumed speed and some assumed measure of the synchronization error. And of course, this easily extends to the same scenario in 3D space, and this can be applicable for all ray combinations where the distance between the rays is not excessively large given our assumptions on the scene and object properties. Now, one step further, suppose we don't have an object or a specific recording, but we want to describe the depth uncertainty as a general property of a planned camera system. So then, instead of specific observations of specific rays, we use this previous solution to map all possible depth uncertainties given some amount of synchronization error and an assumption on the maximum speed of object in the scene. With this way, we can use depth uncertainty and the generalized version of depth uncertainty as an input to the multi-camera system design process. And then, from this generalized model, we can highlight some implications towards setup of multi-camera systems. So, as seen in this figure, camera systems with a parallel viewing direction or non-convergent cameras, they tend to result in a larger depth uncertainty as expected, and thus such camera systems would be more affected by a synchronization error. Since depth uncertainty scales nearly linearly with the increase of maximum object speed and also increase in synchronization error, we can estimate that this view convergence effect seen here would persist for various camera system and scene setup scenarios. So, in brief on that, depth uncertainty is a parameterization of the consequence of imperfect synchronization in a two-camera system. This, of course, relates to depth estimation, which is a common task usually allocated to stereo camera pairs that are used to substitute a dedicated depth sensor. And from this model, we can draw implications or conclusions towards multi-camera system design and gain a sense of whether synchronization error is something that would need to be corrected in a system we would be designing. So moving on, the next contribution to talk about it concerns the design of multi-camera systems or end-to-end systems that are intended for telepresence applications. So multi-camera systems for telepresence or for real-time rendering, they tend to be specialized for a given display or camera technology, where configurations of such systems are usually determined by the sensor data rates that are distributed across computing units or processing threads in an effort to try and optimize the available bandwidth and processing power. The various processes within these end-to-end systems tend to be allocated for specific hardware configurations and applications. And of course, this is a viable approach for solving specific problems. However, this does not easily translate from system to system. And in terms of a multi-camera system framework, this would not easily scale to different configurations. So to resolve this issue, we created a multi-camera system framework that is defined across 3 processing domains: the near camera domain, the cloud domain or the intermediate processing domain, and then the near display domain. Similarly, the tasks that would be expected within a full end-to-end system going from capture to presentation are isolated to specific subdomains or stages based on the purpose of these tasks. Now, this framework was implemented as a test system using a set of computer vision cameras and single board computers as the near camera domain for video capture and also for encoding. And for the test implementation, we used a cloud-based transcoding system for the intermediate processing stage. Also, an open source multimedia streaming library, GStreamer, was selected as the base for the transmission components. in order to verify the feasibility of the framework and also this test system for the use in telepresence applications. A brief overview of the near camera domain principle is shown here, where we have a number of cameras and additional sensors that are all assigned to one processing unit. This, in effect, this allows iterative scaling under changing sensor counts and types. Similarly, the encapsulation of software modules allocated to different stages of processing allows us to more easily adapt this framework to different sensor types and different processing types, where a change in one domain would not trigger a downstream change in the successive domains. And similar compartmentalization was used in the other domains as well. Now, the test implementation was measured for processing latency in the near camera and near display domains in order to verify the framework's feasibility and also to verify the choice of the transmission library. And the test results indicated an acceptable, if not ideal, level of processing latency. In particular, the video compression or encoding, in this case NVIDIA's accelerated H.264 encoder, was the largest source of single component latency in the processing stream, which was followed by the GStreamer framework's image format conversion unit. So overall, this tested framework was designed to decouple the capturing processes from the hardware. And also it was designed to serve as a testbed and a foundation for further multi-view and telepresence systems with varying configurations. We also use this framework as the basis for capture systems in the following contributions, which we will switch into now. So finally, moving closer to the augmented telepresence itself, we will switch to the next contribution, which is a camera and LiDAR-based augmented remote operation system that is considered in the context of an application within the mining industry. So, as mentioned before, remote operation can have significant benefits for the worker safety in industries like construction and especially underground mining. And in such contexts, augmented telepresence could lead to a better awareness of that remote environment compared to straightforward telepresence. At the same time, this context enforces additional constraints, such as the need to accurately display the actual structure of the remote environment instead of showing a realistic looking simulated alternative or an outdated previous recording from an earlier scan or sampling. Now, also, since both cameras and LiDARs are more and more prevalent in similar applications and within this context, we can assume that we can use a LiDAR sensor as a basis for recovering the 3D structure of the surrounding environment. Now, in mining, contemporary remote operation solutions tend to be based on straightforward telepresence, meaning direct transmission of camera views that are mounted on the vehicle without much augmentation or manipulation. However, in other somewhat similar contexts, there are augmented solutions that are typically additive. And by that I mean that extra information is used to insert virtual elements or virtual overlays on top of the existing views as an additional form of information presented to the operator. And in some solutions, optionally, the 3D structure of the environment is shown from another perspective. So for our approach, focusing on the mining context, we decided to use camera and LiDAR data to create an augmented telepresence interface for remote operation that shows novel perspective views of the environment. In this case, in this image, they are labeled indirect views. as well as showing a disoccluded view with occluder removal, which in this case acts as a diminished reality augmentation for that view. And because of the application context that we have in mind, we cannot rely on pre-recorded structures, nor can we use large area in-painting for the disocclusion based on predicted or simulated in-painting patches, because we want to show the actual remote environment as accurately as possible. So a very high-level overview of the rendering process used to achieve the previous interface is shown here. At the core, we are using sparse LiDAR points as basis for the scene geometry depth, which is then used for rendering the novel views and augmented views by depth-based image rendering. This rendering algorithm is largely memoryless, which means that all operations are performed on a frame-by-frame basis without digging into the past frame memory. And also, to avoid bottlenecking, these rendering steps occur in parallel with the frame capture and pre-processing stages, which include LiDAR noise accumulation, or rather accumulation of the LiDAR scan frame. Once we have all the frames from our sensors available, then we perform color-based edge extraction. We perform LiDAR point projection with some pierce-through point removal and edge masking, followed by depth upscaling of the LiDAR depth, which then allows us to use depth-based image rendering and color lookup to generate the final output views. Now, one downside with using a rotating LiDAR as the basis for depth-based rendering is that LiDAR points tend to oscillate in depth from one frame to the next. The figure here shows the 3D position of one point capturing a static scene of a static surface across several LiDAR rotations. And we can see that the point is oscillating along the direction of the laser ray that is emitted by the LiDAR. Now, this oscillation is likely to cause unwanted effects in view generation, such as geometry flickering. So to address this, for a rotational LiDAR, the 360-degree scans are not generated instantly, but they are accumulated from small segments of those scans across time and across the angle of scanning. And this accumulation happens over a period of 100 milliseconds, at least for the LiDAR that we chose, that are accumulated from these smaller segments that are captured as the LiDAR rotates. Now, to reduce this effect of depth oscillation, we decided to use a conditionally weighted combination of the previous and the current scan segment that are available in the LiDAR API at the moment of the update. This solution allows us to have a better temporal consistency from frame to frame, and it also reduces the occurrence of random missing points. And since both of these segments are available at the moment of updating for that segment, we can perform this operation at no additional delay to the overall frame accumulation process. Now, the view generation also requires upscaling of the LiDAR depth. The left column here shows two small patches of the original LiDAR depth that are projected to a 2D image plane that would be used as a depth map for rendering. And the next column here shows how that depth map would look like with simple point splatting. In the next column, we see the consequences of removing the so-called pierce-through points, which are essentially background geometry points that are occurring in between points of a foreground object. And the next column that shows the result of adding an image edge-based constraint to the depth diffusion, And the fifth column shows the result of using both an image edge and a depth discontinuity-based constraint to the diffusion process. So, because this is intended to be a real-time system without preconditioned data, all processing needs to happen in a reasonably low time. At the absolute highest, it needs to happen within the time period that all sensors need to capture a new frame. That would be 100 milliseconds based on the LiDAR that we had access to. In our experiments, the system had a consistently lower time cost for the rendering that was averaging at about 47 milliseconds per frame. And this includes the cumulative generation of all necessary views for the augmented interface. The depth upscaling stages take the majority of that time, up to 37 milliseconds on average. However, this compares reasonably well with other similar approaches that have a lesser difference between the initial and the upscaled depth resolutions. So, in brief, the proposed augmented remote operation system is designed for the underground mining scenario. And the main point of this contribution was to demonstrate the feasibility of an augmented telepresence interface within the constraints set by the underground mining context. And the use of sparse LiDARs, which are increasingly found in autonomous vehicles and are coming down in cost as well. The use of such LiDARs for view augmentation requires the aforementioned filtering and upscaling steps in order to use depth-based image rendering. This does come at a performance cost, but that cost seems to be low enough to attain acceptable rendering frame rates. So finally, we come to the last contribution, considering the user experience of augmented telepresence. Now, if we intend to have an immersive telepresence system for remotely controlling something, then the remote environment can be shown to the user in either a first-person or third-person perspective. That would be like sitting in a cockpit or standing off to the side of the machine that you are controlling. The third-person view tends to provide a better awareness of the surrounding environment, which is good for safety and thus would be preferable for safety-critical applications. However, with a direct camera pass-through solution for a third-person view, this also leads to a lower view mobility, and also the selected viewing position may affect the accuracy of control that the operator has if that viewing position is too far, for example. Further, for providing an immersive control interface, usually head-mounted displays are used. And these head-mounted displays tend to reduce the accuracy of depth or distance judgment in the users, especially in systems with a constrained field of view or a limited viewpoint mobility, and also in setups where people do not get to experience that same environment in reality and through the headset, but only have the headset environment available. So this altogether implies a potential problem in telepresence with systems that rely on immersive third-person viewpoints. So in an augmented telepresence scenario with a fixed third-person view, head-mounted display rendering, and some form of remote controlling a device, problems in this depth judgment might lead to problems in the ability of users to perform the remote control. To investigate this, we focused on two factors, the choice of viewing position and in-view augmentation. And we wanted to explore how these factors affect the user's remote controlling ability in augmented telepresence. Now, to address these questions, we performed a task-oriented quality of experience study with non-expert participants in a controlled lab environment. Specifically, quality of experience is defined as the degree of delight or annoyance of the user of an application of service which results in the fulfillment of the user's expectations with respect to the utility and enjoyment of the application or service in light of the user's current state, which becomes somewhat relevant when we are dealing with head-mounted displays. So to address these questions, or rather to investigate these problems, here we set up a test system where we have two stereo camera pairs providing a third-person side view and an overhead view perspective of a remote control environment. This side view is closer to a physical out-of-cockpit driving for crane vehicles. However, the overhead view requires less of a dependence on depth perception to navigate to each of the targets highlighted in blue in this figure. Now, the task that is enabled by this system is sort of a reach and touch task, meaning that the user would use the remote control to control the vehicle to drive it to a selected target and use the arm to touch the target as accurately as they can. Here are the three augmentations that we used in the study. The first one is a control augmentation that only highlights the active target that the user must reach. And then we have two assisting augmentations, grid and box, that indicate how far the remote control crane is from the active target. Now, all these augmentations that are attached to in-scene objects, like the target indicator, they are rendered stereoscopically because they need to be consistent with the displayed camera views in order to not provide a conflicting depth cue to the user. So to summarize the test design, we set up an experimental task for participants to use the remote-controlled vehicle to drive to and touch as many targets as possible in a single 2-minute run. We used 6 test runs to cover each combination of augmentations and views that were available. And of course, both the run order and the order of targets picked within each run, they were randomized. For assessing the state of the users during this quality of experience assessment, we used the 16-symptom simulator sickness questionnaire by Kennedy et al. And then for assessing the quality of experience, for each run, we gathered the participant's subjective opinion in a linear scale of 1 to 5, focusing on the subject opinions on their task accomplishment, the perceived task difficulty, and then their perception on viewpoint helpfulness and the augmentation helpfulness for that run. And then we also tracked the objective task performance through the number of targets reached in each run, the time taken to navigate to a target, and then the time taken in the target vicinity. And also we measured the accuracy of each touch to get a sense of how well the users were able to complete this task. So we performed the investigation on 27 non-expert participants, and in the subjective results, we saw a more significant difference between the viewing positions in all of the subjective metrics, all of the 4 subjective scales that we measured. The difference between specific augmentation designs was somewhat less pronounced. However, the depth-aiding augmentations were rated as fair to good by the participants, which implies at least some perceived positive benefit. Then in objective results, we saw, again, a significant difference based on the viewing position available across all runs. However, we did not see a significant effect on the objective metrics from the augmentation design. So overall, with this investigation, we demonstrated the effect that a viewing position has in a third-person augmented telepresence. Specifically, a poorly selected viewing position can cause a significant loss in subjective experience and in task performance, particularly when users are forced to rely on their depth perception in head-mounted display interfaces. Now, position assisting augmentations may mitigate this negative subjective effect, at least from some viewing positions. However, the viewing position effect seems to be dominant. So now that the specific contributions have been introduced or summarized, now it's time to conclude this overview. So looking back at the overall goal of this work, the main purpose was to explore how should multi-camera or multi-sensor systems, how they should be designed for use in augmented telepresence applications, and also how is the user experience affected by applying augmented telepresence in non-entertainment contexts. So I think the contributions presented up to now map to these goals in the following way. The first three contributions on calibration, synchronization, and the multi-camera framework, they concern the production of knowledge that informs the design of multi-camera systems. That information then propagates to the two end-to-end telepresence systems that were involved in the latter contributions. And these contributions in turn are focused on the user experience and on the system design specifically for augmented telepresence. Now, of course, we don't have a complete exhaustive cover of every single aspect involved in the whole camera-to-human chain. However, with these contributions, we are at least sampling and filling knowledge gaps that were found in different aspects and different layers of this extensive range. So finally, regarding future work, there are some direct and some not so direct follow-ups that could be pursued. The most obvious direct extension is to conduct a quality of experience study based on the remote operation system that we designed for mining, and preparations for that user study are already on the way. Secondly, the depth uncertainty model as it was produced today, it could be extended to incorporate more camera parameters such as a line exposure offset also, or rolling shutter, and possibly some motion blur detection. As well, this model could be extended to triple camera or multi-camera setups to attempt and reconstruct object trajectories, and this would then convert this predictive model, this descriptive model, into a predictive model that would lead to classification, detection, and possibly prevention of the synchronization error. And then there is the indirect follow-up caused by the quality of experience study, which would be an investigation on prioritization of augmentation designs based on visual appearance or task performance. Because in our study, we saw a difference between the subjective perception that participants had and the actual performance metrics, their ability to complete the task as was given to them. And then it's not yet clear whether an augmented telepresence interface, and specifically the augmentations therein, whether they should prioritize the subjective experience or whether they should prioritize the task performance. So with that, I conclude this summary and this presentation. Thank you all for your patience, time, and attention.
Thank you very much, Elijs. So this concludes the first part of this dissertation and defense. So we will now have a break for about 5 to 10 minutes, and we will continue the discussion led by the opponent afterwards. So you can stretch your legs a little bit while we take a small break here.